Day 3, we're going to look at reading graphs and function notation. Here are the graphs of some situations you saw before. Each graph represents the distance of a dog from a post as a function of some time since the owner left to purchase something from the store. Distance is measured in feet and time is measured in seconds. So let's see if we can read our graphs of the functions. Number 1, use the given graphs to answer the questions about each of the 3 days. Number 1, how far away was the dog from the post 60 seconds after the owner left? So we'll start with identifying 60 seconds. We'll go up till it meets our function and then go over. So for day 1, that would be 4 feet away. For graph 2, 4 feet away. And for graph 3, so the dog is 4 feet away from the post each of the days that we're looking at the graphs. Number 2, how far away was the dog from the post when the owner left? Okay, so when the owner left was at time 0, and so we can see that here it's 1.5 feet for day 1. For day 2, 1.5 feet. And day 3, 1.5 feet. The owner returned 160 seconds after he left. How far away was the dog from the post at that time? Okay, so 160 seconds. So we would say for graph 1, estimate maybe like 3.7 feet. For day 2, it would still be 4 feet. And day 3, maybe about half a foot away. How many seconds passed before the dog reached the furthest point it could reach from the post? All right, so we have a lot going on here. Whoopsies, let's erase. All right, so time that's furthest away. I'm going to use blue. And for day 1, it was 5 feet away at about 50 seconds. At day 2, 5 feet away at like 38 seconds, 37 seconds. And then day 3, 5 feet away, like almost right away. I don't know, maybe around like 8 seconds. Consider the statement, the dog was 2 feet away from the post after 80 seconds. Do you agree with the statement? Okay, so the dog was 2 feet away after 80 seconds. Let's use pink. 2 feet away after 80 seconds. Okay, so let's go to 80 seconds. I mean, he was 2 feet away. It was further than 2 feet away. So we could say yes, greater than 2 feet for the first one. If we had to estimate, maybe like 2.5 feet away. So, well, this says, what was the, okay, no, I put that in the wrong spot. So the dog was 2 feet away. I mean, greater than 2 feet. It wasn't exactly 2 feet, so this was greater than 2 feet. How about day 2? And what was it, 80 seconds? I mean, at 80 seconds, he was 4 feet away here. Oh, okay, so that would be for day 3. Day 3 is the one he's exactly 2 feet away. So yes, I would agree with this statement for day 3. And then number 3, what was the distance of the dog from the post 100 seconds after the owner left? Okay, 100 seconds after the owner left. So in graph 1, it's about 2.3, 2.4. Day 2, at 100 seconds, it was 4 feet. And day 3, it was about, I don't know, 1.3, 1.4 feet. So what we've done here is we looked at graphs of functions and we were able to read the graph to answer the questions. So today we're going to look at function notation, which will be a shorter way of asking all of this. Like if you notice, this is pretty wordy, and we can actually use this thing called function notation to ask the same questions. So for function notation, here's the intro. Let's name the functions that relate the dog's distance from the post and the time since its owner left. So we're going to call the function f for day 1, g for day 2, and h for day 3. The input of each function is the time. Okay, so the input, the thing in the parentheses, is the time. Describe what each function represents. Okay, so f is day 1, so day 1, and we're looking at the distance of the dog 15 seconds after its owner left in day 1. So this is day 1. We want the distance after 15 seconds, or at 15 seconds, we can say. Okay, so this is a much shorter way of writing it. F of 15, what's the distance at 15 seconds? G of 48 would be what's the distance on day 2, so day 2 distance at 48 seconds. And then C would be day 3 graph at time t. Number 2, the equation g of 20 equals 4 can be interpreted to mean on day 2, 120 seconds after the dog owner left, the dog was 4 feet from the post. So this one actually gives us the answer after 20 seconds on day 2, 4 feet away. What does each equation mean in this situation? All right, so H was day 3. After 40 seconds, the dog was 4.6 feet away from the post. Put away. Okay, F of t. So this is saying, all right, at time t for day 1, so day 1, time t, the dog was 5 seconds away from the post. And we could actually go back up to the graph and solve for t. And then g of t saying, all right, day 2, at time t, the dog is d feet away. And this is function notation. Again, a shorter way of saying all these words, but in an equation. So let's do some examples. For birthdays, Rule B gives a person's name as the input and gives their birthday as the output. Rule P takes a person's name as the input and gives their birthday as the output. Can you complete each table with 3 or more examples of input-output pairs? All right, so we go around in class and ask, right, what is your birthday? So for example, we have Jameer. His birthday is October 4th. And we have Zamir. His birthday is October 8th. We have Charlie. His birthday is October 18th. And Louisa, her birthday is also October 18th. All right, Rule P takes a person's name as its input and gives their birthday as an output. So for example, we could say, all right, who was born on October 4th? That would be Jameer. Who was born on October 18th? Ooh, that would have 2 outputs. That would have Charlie and Louisa. Complete each table with 3 or more examples. Okay, I kind of did that. 2, if you use your name as the input to B. Okay, so B is the first one right here. How many outputs are possible? Okay, so if I use my name, like Mrs. Bajan, I have 1 output. I was born on June 10th. So I have 1 output. If I use my birthday as input to P, how many outputs are possible? All right, so this is saying, like, what if we used October 18th? And we can see that, okay, there's going to be more than 1 output. There's probably many people that were born on October 18th. So there could be many people born on a certain day. Only one of the 2 relations is a function. The other is not a function. Which one is which? Explain how you know. All right, in the function, definition of a function is for every input, there's only 1 output. So the function would be this first one, Rule B, because again, you have 1 input, a person, and they have 1 birthday. So that's what a function is. For every input, there's only 1 output. For the relationship that is a function, write 2 input-output pairs from the table using function notation. All right, so this is function B. All right, so B of Zamir would be October 8th. the birthday of Jamir would be October 4th. All right, summary. Here are graphs of two functions. Each function represents the cost of riding in a taxi from two companies, Friendly Rides and Gray Cabs. For each taxi, the cost of a ride is a function of the distance traveled. So the cost depends on the amount traveled, the distance traveled. The input is in miles and the output is in cost. The 0.2579 on one graph tells us the cost of riding a Friendly Rides taxi for 2 miles. The 0.2425 on the other graph tells us the cost of riding Gray Cab's taxi for 2 miles. We can convey the same information but more efficiently by naming them using function notation to specify the input and output. All right, so we're going to name the function for Friendly Rides F, and Gray Cabs will be G, and we're going to okay, so this is just showing us like how they did it. So F of 2 just means after 2 miles, what's the cost? G of 2, what's the cost for the second cab fare after 2 miles? And again, it's just explaining how they got the numbers. So in general, function notation looks like this. F, and then you have parentheses and an X, and we call this F of X. So it can be F of X, G of X, B of X, parentheses is of. The function notation is a concise way to refer to function notation and describe its input and output, which can be pretty useful. So we're going to practice this idea of function notation. Number 1 on your assignment says the height of water in a bathtub, W, is a function of time t. So WT, the water over a certain time, and P, okay, they want P to represent your function. Okay, so P of t. Height is measured in inches and time, okay. Match each statement with its function. P of 0. What's the height of the water at 0? The bathtub starts with no water, so you're matching it up. Okay, so really the assignment today is, can you use this idea of function notation, interpret it what it means, and solve? So your assignment will just be page 11.